Yeah, we're seeing your slides as I think we should. So I think we're all good. This looks right. I think it should be fine. I don't think we're gonna get any better because it's Zoom. So
The slides, yes.
yeah. Okay.
I guess people are gonna go to see it.
Okay. Okay.
Or does that look okay?
It's good. Yeah, that'll be good. Oh,
Sorry, now my whole screen is messed up on my end.
you guys just give us like 1 minute. We're working through some technical issues with Zoom, as always.
Okay,
That looks good for us.
that looks good. Okay, then let's do that. Okay.
Okay, perfect. Hey, everybody.
Okay.
To start this session, we have Marina and Gemma talking about what meteorites can tell us about extrasolar system chemistry. So Marina, take it away.
Okay. Thanks everybody, and thanks for bearing with me with the Zoom difficulties. I wish I could be there in person, but I am currently analyzing particles from asteroid Ryugu at a synchrotron right now. So cosmochemistry waits for no one. That being said, I am a planetary scientist in this session, so thank you for having me and listening to me talk about meteorites. I'm a postdoc at Stony Brook University, and I've spent a lot of time thinking about element abundances and their variations in our own solar system. And I think there's a lot that can be hopefully useful for you as you start to look at extrasolar systems and explore their chemistry. So I like the idea of kind of starting with this image from ALMA because I kind of see it as a visual representation of the idea that this incredible amount of information we have gleaned remotely from telescopes can be kind of grounded with the extraterrestrial material we have delivered to Earth in the form of meteorites. So in the broader context, I hope what I'm sharing today is applicable and helpful in reviewing what we know about the abundances, condensates, and chemical relationships in our own solar system, and focus on how we can apply these concepts to understand the chemistry of extrasolar systems. And for the purposes of this Splinter session, I'm particularly focusing on the motivating questions of how we can determine formation history of an object from observational data, and what chemical abundances do we expect to see in stellar companions. So if we look at our own solar system, we can start with this canonical idea of the protoplanetary disk, right? The gas and dust left over after the formation of the sun. And we know that this protoplanetary disk eventually formed and evolved into the solar system architecture that we see today. Of course, we have the 4 rocky planets, the asteroid belt, the gas and ice giants, and then the Kuiper belt objects. And I study the link between the protoplanetary disk and this solar system we know today. That is the meteorites, right? So preserved in the asteroid belt and probably in the Kuiper belt, although we maybe don't have samples of that just yet. But these meteorites tell us what kinds of processes were happening as the planets were forming, and they preserve both chemical and physical information from this time period. And most of the samples that we have here in collections on Earth come from asteroids, which are of course concentrated in the asteroid belt, which you can think of as the debris field left over from the time of planet formation. And now that we're able to kind of explore extrasolar systems in increasing detail, I think it's more important than ever to utilize the extraterrestrial material we have at our disposal to understand how we evolve a protoplanetary disk into the diverse set of planets we have today. And this is kind of where my sales pitch for meteorites comes in. Again, I'm just trying to drive the point home that these primitive materials preserve both chemical and physical information from the time of planet formation at resolutions far beyond what we can ever hope to explore remotely. So I think gleaning as much information as we can out of these samples is really, really useful for the future of not only planetary science, but extrasolar system science as well. So I always like to include a picture of meteorites in my talk because I realize that most people don't spend their days staring at these rocks. So this is probably one of the most famous meteorites we have in collections. This is a Yende, it fell in 1969. And this is the hand sample. So this image is approximately the size of your palm. And if we were to take this meteorite and we wanted to get at its bulk chemistry, what we would do is we would pulverize it down into a fine powder, dissolve it in acid, and put it into a mass spectrometer. And once we get the data off a mass spectrometer, we can take those measured abundances, which I've shown here on the y-axis, and plot them against the element abundances measured in the solar photosphere, which I've shown here on the x-axis. And what you'll see, with the understandable exception of carbon, nitrogen, and oxygen, is that there is a one-to-one relationship between this primitive chondritic material and the bulk element abundances we see in the solar photosphere. So in other words, the chemistry of these primitive planetesimals, right, matches that of the sun. And in Shannon's talk in the last session, he kind of mentioned, you know, assuming that the magnesium to silicon ratios of companions are the same as that of their star. And here I'm giving you an empirical reason to make this assumption, because we can actually measure and see that the major, trace, and even least abundant elements in chondrites have a nearly one-to-one relationship with the solar photosphere. So we've established this relationship and this link for our own solar system. And, you know, since this is really our only evidence point that we're going to have at this level of detail, I would argue that we can expand this relationship and apply it to other systems as well. So having that understanding of the bulk chondrite abundances and the abundances in the solar photosphere, we can start modeling or even use that information to check our models and examine the condensation sequences, basically what species or what minerals we expect to condense in astrophysical environments, given these starting compositions. And we can explore this at a variety of temperatures and pressures and see what that does to the expected condensate species. And this is a fairly complicated diagram that I have attempted to simplify for you guys here. Here I'm showing an assortment of minerals. All of these are observed in chondritic meteorites. And I'm showing their condensation temperatures, essentially. So the temperatures at which we expect these minerals to solidify. And initially, we expect the most refractory minerals to solidify. These are calcium, aluminum, and titanium-rich minerals, of which there are a wide variety, and that are followed then by iron, nickel, metal, and then the magnesium silicates. And you might be familiar with these species because you also see them in expected condensation sequences for brown dwarfs. This, of course, is from the, oops, I have the reference wrong, the Lauders 2004 paper, not 2003. But what we see is the same kind of condensation sequence, except now the temperature axis is inverted because we're not going from cold nebula to solid minerals. We're kind of going deeper in the atmosphere of these objects. So perovskite and corundum, of course, are these calcium, aluminum rich and titanium rich minerals, and they are followed by this iron metal liquid, and of course the magnesium silicates. So starting with these initial compositions, we can start getting at a lot of information of the minerals and the abundances we expect to see given these initial conditions. And with chondrites in particular, because we can investigate them again at increasingly fine scales, we can get at we can quantitatively get at mineral abundances that we would expect in these systems. And again, this is a direct line of evidence of the expected condensates that we would see given a disk of solar composition, which is what we have in our atmosphere. So this is just one example on the right of a pie chart of mineral abundances in a chondrite, and you can see that they are, the chondrites are very much so dominated by olivine and pyroxene minerals, with metal and then the calcium and aluminum rich species following. So I'm going to try and tie it in then to a figure from Emily Calamari's paper. This is our work published earlier this year, and Shannon showed this in the previous session. So in case you didn't see it, right, we're getting at this question of how can we predict what our silicate regime is given an initial composition. And in this figure from this paper, what we did is we looked at the magnesium to silicon ratios that you might expect given a particular stellar abundance, and see how that ratio would affect what silicates we expect to be able to observe in companion objects. So at below a magnesium to silicon ratio about 0.9, you would expect to see enstatite and quartz dominated regimes. And above that threshold, you would expect to see enstatite and forsterite dominated regimes. And I've annotated this figure to show the solar magnesium to silicon ratio, which is at about 1.03. And this, of course, puts us in the enstatite and forsterite dominated regime, which is verifiable by the fact that we see enstatite, so that's the magnesium-rich end member of pyroxene, and forsterite, the magnesium-rich end member of olivine, as the most abundant mineral phases in these primitive meteorites. So on this kind of broad level, looking at the bulk system chemistry, I hope you can believe, I guess, my argument that stellar abundances are definitely giving you your predicted condensation sequences given a particular temperature and pressure. We can also get at relative mineral abundances just from these stellar or solar abundances. And you can also get at the predicted silicate regime of a certain system. So I think these are extremely valuable parameters that you would want to know for any given system. And the meteorites we've studied in our own solar system are really the kind of empirical reasons why we can start applying these kinds of relationships to other systems. If we begin to explore the solar system, though, at a finer scale, things start to get slightly more complicated. So this is a kind of cartoon cross-section of the protoplanetary disk. So far, I've been talking primarily about carbonaceous chondrites, which are the most primitive type of meteorite we have in collections. These are thought to come from the outer solar system, are generally richer in volatiles. But if we start to consider the non-carbonaceous chondrites, which are a little bit less primitive than the carbonaceous chondrites, we start to see more variability in the chemistry. And so this starts to kind of give you a better understanding of chemical variations within the evolving protoplanetary disk. And so if we measure particular chondrite groups, on the left, we have non-carbonaceous, and on the right, we have carbonaceous chondrites. We can see that the less primitive meteorites on the left-hand side show chemical variations given an orbital radius. And I want to emphasize that the groups on the x-axis, the order of them is completely arbitrary. So the only real designation here is that we know the non-carbonaceous meteorites come from the inner solar system and the carbonaceous come from the outer solar system, but their order within those two groups is up for debate. But we can see that these primitive carbonaceous chondrites are consistent with the solar photosphere abundances, whereas the non-carbonaceous, more evolved chondrites start to vary. And getting at why is an ongoing issue and problem in meteoritics, and something that I'm very interested in exploring. We can look at element ratios beyond magnesium and silicon. So this is kind of a lot to throw at you right at the last minute, but you can see that there's variability in other element pairs as well. And what that means for the chemical evolution of the protoplanetary disk, I think is a very, very interesting question that we need to explore more detail, especially as we're trying to now understand the chemical variability in exoplanetary systems. Very quickly, I think also the variation of C to O across the protoplanetary disk is something that meteoritics also can kind of help put a pin in. We do see mineralogical evidence for C to O variation across the disk. In particular, the non-carbonaceous chondrites, again on the left-hand side here, we think come from more reducing environments compared to the carbonaceous chondrites. And we see that mineralogical evidence with increasing C to O ratio. So where you have more carbon, less oxygen, you get more carbon-dominated mineralogies, and that evidence is seen in meteoritic minerals. So in summary, I think meteorites can give us a wealth of information. Most notably, I think in this context, that the bulk chemistry of primitive meteorites is reflective of that of solar chemistry. We also see that they record C to O variation across a protoplanetary disk. And there are isotopic and elemental dichotomies within the system, which I think need to be explored in more detail. And there are also the empirical verification we need to start applying these mineral condensation sequences to other stellar compositions. And so applying this now to the extrasolar system chemistry, I think the main takeaway is that the bulk chemistry of initial accreted solids will likely match that of the stellar chemistry of the system. I think there's also something to keep in mind is the C to O variation across the protoplanetary disk and how that can affect particularly the rocky materials that form in exoplanetary systems. I think an open question is what is the degree of isotopic and elemental dichotomies within the system? And of course, I think perhaps the most hopeful is that we can create condensation sequences for each stellar system given its stellar abundances, if we have that. So I know this is a lot to throw at you. I'm happy to take any questions, and thank you for listening.
Time for one question while we get Julie set up. Same here.
Okay, great talking. So I wanted to ask if I'm not a huge a lot about meteorites, but would this same thing, this one relationship, like be applicable to like stone time, or is it just pure like stone type meteorites?
My audio isn't great. I think the question is, do these relationships apply to non-stony meteorites? Is that correct?
Yeah, like stone time.
Okay. Yeah. So in this talk, I'm exclusively talking or referring to chondritic meteorites, which come from undifferentiated planetary bodies. And all of the iron-bearing meteorites that I think you're referring to would be what we call differentiated meteorites. So that comes from evolved planetary bodies that have separated into a core, mantle, and crust.